So to talk to you about Open Notebook Science and specifically the role of cheminformatics in terms of storing information and in terms of retrieving it. So first, a little definition. What do I mean by Open Notebook Science? Well, if we look in the past couple of years, there's been a movement towards making the scientific process more open. And I like to use this little chart here to show where we've come from and where we're going to. In the traditional lab notebook, for example, you have everything is unpublished unless somebody makes an effort to put the data together and then send it for publication. But if they don't do that, everything, including the failed results, are not going to make it to anybody. All right. So as we move along this arrow here, we have traditional journal article. So in that case, it's less closed in that more people can have access to the information. But again, it doesn't include a lot of the elements such as the failed experiments or the view of all the experiments that have been run in a given project. Something that's come up lately a lot has been open access journal articles. And here we're talking about articles that can be accessed for free by anyone. And typically the author or a third party will pay the cost of that. So that's good. It's making things even more open. But again, these still have the traditional journal article format. So what we're talking about here in Open Notebook Science is full transparency in the scientific process, where actually the lab notebook of my research group is made available in real time using a few different technologies which I will discuss. Okay, so to give you sort of a background of where we are, my group at Drexel, we're a synthetic organic group. And by doing these things openly, we need collaborators, obviously. And one of the greatest benefits of doing Open Notebook Science has been to find some great collaborators. Rajarshi here has been a very active collaborator of ours, and he's been doing docking for us. And we've had people who've tested our compounds. Lately, Phil Rosenthal has been testing our compounds for anti-malarial activity. So most of what I'll be talking about today is in the context of anti-malarial agents. We've also, though, tested a few compounds for anti-tumor activity. Okay, so what I'm going to do in the remainder of my talk is give you screenshots of the various tools that we use and how they fit together. So we have a blog, we have a wiki, we use Google Docs, mailing lists, we use ChemSpider, and we use CDD. And all of these talk to each other. And you'll notice that all of these are free hosted services. And that's really important for me because if we have people who think that what we're doing is a good idea, they should be able to replicate it for no cost and with minimal effort. And because these services are free and hosted, you can in fact do that. Okay, so I like to start the story with the blog. And the blog, we typically report things such as milestones or larger problems that we've been having. So there's not any hardcore experiments in the blog because that would be very monotonous and nobody would read it. So we put things that are more interesting to a broader audience. And so here I'm talking about how we're targeting this enzyme falcipain 2 that Phil Rosenthal is testing for us, malarial enzyme. And I'm talking about all kinds of things. And here I'm linking to experiment 150. Now this is actually a link to the wiki that is the lab notebook of that how this compound was actually made. All right, and so where I'm talking about this compound here from this Yugi reaction. And here's a nice picture of a crystal of it. So when I click on that link, it takes me to a pretty long page. So I'm going to look at different sections of it and show you where information comes from, and I'll try to focus more on the cheminformatics aspects of this. But essentially, if you go on this page, you should be able to link to a summary post that sort of explains the bigger picture of why we're doing this, because someone might have fallen on this page just by doing a Google search. And it has a whole explanation of everything, including the molecule. So if you want to click on this link, this Yugi adduct, it will actually take you to the ChemSpider entry for that compound. And Tony's already been through how great ChemSpider is, and it is, right? And it's got all kinds of information that his servers calculate so that I don't have to. And that's a huge benefit for a group like mine that doesn't really have a lot of computer science people. I mean, we're synthetic organic chemists. So we can also link to the experimental plan of the experiment. And we can link to the docking procedure. So Rajarshi was talking about, storing the procedure in such a way that other people would be able to reproduce it. And that's what we try to do as much as possible. So again, this is just as a wiki page. So we're linking to the library, we're linking to information on the enzyme that we're docking against. Rajarshi actually wrote this, and these are the results. And if we click on one of these result links, we end up with a Google Doc that has just a list of smiles in the order in which they were docked with the enzyme. So this is still falsipane 2 that we're looking at. And so Rajarshi is saying, these are the top 10 compounds that we should probably think about making. So that's what we've been doing. We've been getting feedback from the people doing calculations to decide which compounds to make next from our virtual libraries. And we also have a procedure section. Okay, so there's some redundancy here. The idea here is to write up the information in such a way that it can be quickly copied and pasted when we submit some of this work for publication in a traditional article. So what I'm talking about here is not a way of bypassing the traditional system. It's just a way of getting the information out there much more quickly. Okay, but we're still, following that plan of submitting to traditional articles, and this is, of course, the format that it would look like. Okay, so again, part of that page, there's a results section. And here, instead of just linking to the NMRs as PDFs, we actually link to them as JCAMP, in JCAMP format. And we use JSpecView, written by Robert Lancashire, fantastic free program that allows you to view NMR spectra or any spectra in JCAMP format in a browser in a way that can be expanded very easily. So this here is what the spectrum might look like in a PDF, in a supplementary information section. I know a lot of you are probably annoyed. You want to find out what the NMR look like, and you get this PDF that was scanned, and you can't tell what the peaks look like. But if you have actually the raw data in JCAMP format, you can easily expand this little peak and see that yes, it is a triplet, and you can measure the coupling constants, or you can do whatever you want with it. And that's really, really important. If you're making statements about things, people have to be able to verify your raw data. They have to be able to make the same conclusions based on the same information. And JCAMP is really a nice little format to use. We've done a couple of things with it. I had a grad student last year write Excel VBA, where we basically monitor reactions, and we would basically give the start time of the experiment, and then Excel VBA would run, and it would calculate all of the different concentrations over time. Of course, you had to assign the peaks. You had to tell which peak corresponded to which compound. But it could then automatically print out a kinetics run for the disappearance of some compounds and for the appearance of other compounds. So those are some of the neat things that you absolutely cannot do with a PDF of an NMR, right? So it's very, very useful to keep it in that format. And as you saw Tony talk about, we've also been using ChemSpider to archive characterized compounds. So the difference here is that these are spectra that I approved of. All right, these are final isolated compounds. But of course, in research, you take monitoring runs, you take impure compounds, you're in the process of purification. So all of those NMRs and spectra have to be accounted for as well. So right now, we're only using ChemSpider to store the best stuff, the stuff that we would send to a paper. And the next thing that we're about to do, we've almost got this done. I'm working with Andy Lang, and we're using Second Life to actually display NMR data. And this will read JCAMP, and it'll do so in a way where you can actually expand the spectrum. So right now this is actually working, but for a spectrum of a fixed x-axis, but we're working so that you can talk to the spectrum and tell it to expand. And so we've almost got that done, and I think it's just going to expand the capabilities of Second Life. I'll be talking about Second Life tomorrow. And actually, ACS Island is going live tomorrow at the SciMix, so hopefully I see some of you there. All right, another section of this page. Again, I'm going through this long, long page that's one experiment. Is that there has to be a log. So we can actually construct the rest of the experiment based on the log, but without the log, we can't do anything, right? Because you can't remember what you did exactly when you added things, exactly when you measured them. So this, something I keep trying to reemphasize to my students, it's absolutely critical that you keep a proper log, because later on you can do whatever you need to do. So when I say that our experiments are in real time, what it means is that the log has to be up, by the end of the day. The other sections of the experiment can, take weeks to actually get uploaded. So finally, when you come to the conclusion section of this article, it says this InChI product was obtained 59% yield. You don't have to take our word for it at all. You can go back and reinvestigate every single aspect and the arguments that we made. Okay, so now comes to storing and retrieving information. This is where the cheminformatics come in. So in order for us to retrieve, compounds and experiments, it's been kind of a challenge, and we've used a tag section. So at the very bottom of each blog or wiki page, there will be tags. And we could use a number of things for this. We could use smiles, for example, but we chose not to do that because there are multiple smiles for a given compound. So we've been using InChIs, and that's worked well for small molecules, but the reality is that for very large molecules like our InChI products, the InChIs are not indexed properly by Google. And so what we've started to do in the past couple of months is use these InChI keys. And we used ChemSpider to provide the service to generate those InChI keys based on either the InChI or the smiles that are submitted to it. So, and these links here of the common names, those are for human readability, and when you click on them, it takes you to ChemSpider. So that's how everything is connected together. So that when you do a Google search with this partial InChI key, it will come up with all of the different experiments where we use that compound. And if you're going to do this, you have to remember to click this repeat search with omitted results, because Google will assume that you're not interested in results if it comes from the same domain name. But we are, because that's the point of this, right? We want to get all of the experiments. Now, you can do a lot of tricks with Google. For example, if you're familiar with the Google Co-op, also called Google Custom Search, you can take all of our blogs, wikis, all the pages that we've generated, and we can actually create a special Google search that will only look on our approved pages. And if you do that, then you have a way of searching a very rarefied part of the net. So all that is available, totally free. Anybody can do this. So how are people actually finding our experiments? Well, I have yet to actually catch someone using an InChI key to find an experiment. So this is something moving forward that we're going to be doing. But I think it's very, very interesting to see how people are actually finding our experiments through Google. So it falls into 4 different categories. It could be specific compounds. So someone might be looking for the NMR of TFA. If they do that, they're in luck. We have lots and lots of NMRs of TFA. It could be a molecular formula. They could just be searching for T-butylamine. Just tell me everything that you know about it. And I'm sure they're going to find ChemSpider hits with that. But people are clicking on these links when they're finding it. It could be experimental conditions. And this is actually really important, because a lot of this stuff is like side reactions of imines. If you search in the traditional literature side reactions, how can stuff not work? You typically don't find that there. But of course, most of the typical lab book is almost all failures, right? So you're going to find lots and lots of stuff that doesn't work. And that's the point. If someone was searching for kinetics of the Bach protection, they will also be in luck. We have lots of kinetics analysis of that. So the other thing that they can find at a higher level is, I talk a lot about educational things. So if they're looking for free downloading chemistry video, we've got that. If they're looking for 3D periodic tables, it's something that I've discussed. And people are looking for that. And also some people are looking for bigger picture, like lysosomal targets, cheminformatics project proposals. So I've discussed the proposals that I've put in, and that's great. I mean, somebody who was looking for that would have actually found it. And of course, you can also search these experiments just by the traditional table of content style. Okay, so now if we want to use this information in a much more meaningful way, we want to be able to compare different experiments. And as you keep doing experiments, it becomes more and more difficult to keep in mind everything that's been done. So again, we're using tools as they become available to us. If somebody comes to me after my talk and volunteers to run a database with this, I'd be very happy. But right now we're using Google Docs because it's simple. We don't have a lot of results to track, and so it makes sense. But of course, at some point it should be imported into a real database. But basically here, we're each one of these rows is one of these experiments. of these Yugi reactions. And one of the things that we observe that sometimes we get a precipitate and sometimes we don't. If you get a precipitate, that's great because you can just filter it and you can scale it up and you can do a lot of things. If you don't get a precipitate, you would have to run chromatography, and that would really complicate things and make it very difficult to scale up. So one of the things that we've been looking at is, can we predict which Yugi product is actually going to precipitate? And so in order to do this simply, everything is put in this table that's publicly available, and then people are free to run models on this. And I'll talk about that a little bit later. Well, now actually. Rajarshi has built models to actually predict going forward compounds that we have not tried to make yet, and he's predicting right now in the next 100, in the list of 100 compounds that we're scheduled to make, he's predicted these 3 should be precipitates. We've also collaborated with other people, Misa Analytics. They've also just this morning actually run a model and have co-predicted that this compound should precipitate, but have predicted another compound that Rajarshi did not precipitate. So again, as he was talking about, it'd be really nice to have ways of comparing models to each other and to do that in a very systematic way. So again, an example, as long as we keep putting things, keeping things completely open, it makes it very easy for people to participate and collaborate with us. Now, going forward, I show you that log, and there are no rules for that log except that they have to record, my students have to record what they do, when they do it, and what they observe. Okay, but they're not required to type any special words or anything. So the problem with that is it makes it really difficult to convert that into a format that a machine could use, or you couldn't readily extract that and put it into a database. So one of the things that we've been doing in the past few months is actually rewriting our logs in a format that should be machine readable. So here I have a series of steps, workflow actually, where you're allowed to add something, you're allowed to wait, you're allowed to vortex, you're allowed to take a picture, but you can't do anything else. Okay, so we have words that we've defined meaning certain things. We have parameters that we specified, and so for example, we specify the molecule using the InChI key, and we'll also specify with a common name so it's human readable. But essentially, that's just something that we decided to do that way, for a bunch of reasons. But there's no reason that it has to be done this way. If somebody wanted to convert this and have the smiles, they could do that easily. They would just scrape the information and then convert it. So this, I think, going forward is going to be very important, especially as we start to gather more and more information. And so looking at these results, we can also compare them. This is a little bit different than the table that I showed you earlier, where we're looking for precipitates or no precipitates. These are actually individual results from experiments that are stripped out and left to stand on their own. Okay, so we would mix compounds together and then wait 4 hours and then take a picture. Okay, so that's not the whole experiment. That's just the first data point. And then we would take it 8 hours, and we would take it 12 hours. Now, if something bad happens on the 12th hour, let's say the student drops the sample, well, we would call that an aborted experiment, right? And everything in that experiment would probably wouldn't be worth going through and digging through it. But if we extract every individual result as something that's addressable and mineable, then it really doesn't matter what happens down the road. So somebody who may not be interested in the Yugi reaction whatsoever may just be interested in, all the reactions where an amine is reacting with an aldehyde. They would find that here, and they would not get any interpreted information. They would just get a picture of what that looks like. What does this look like if I mix it together and wait 4 hours? So that's kind of a strategy that I've been using to get a lot more information that's going to be much more machine readable and machine crunchable. A few things about a wiki. When we first started to do this project, we used a blog actually to record experiments. And it turns out that a blog is really not a great tool for this, because if you change an entry, you have no record of it. You can't tell if it was changed even, or who changed it. So with a wiki, you can see all the recent changes in it. You can look at a specific page. So this is experiment 150 that we've been looking at through all this time. And I can see all the different versions, and I can see who made the changes. I can compare any two versions, and using wiki spaces, the new stuff shows up in green, and the stuff that was deleted shows up in red. I can use the wiki as a way to organize results to explain something that is extremely difficult to publish failures. So here's a little story about the synthesis of dopal. And we tried to make this compound. We eventually did make it, but we failed trying to make it in some really interesting ways. And so this is just the story of that, and it's got links to the papers we tried to use that had wrong information. And so it's just basically explaining all of that. And I think that that can be useful for synthetic organic chemists. And it's typically not something that you make public. We also use a mailing list, which turns out to be really handy for collaboration between groups. So my group will use the wiki almost exclusively, but when we collaborate with people who do docking or people who do testing, the mailing list appears to work pretty well. The other piece of this that we just started to tap into is CDD, Collaborative Drug Discovery. So Drexel University now has users on here, and this is a way for us to basically store and retrieve our assay results. It turns out that 2 of our compounds are active against falcipain 2 and are active to prevent the infection of malaria. And they're not terribly active. They're about 2 orders of magnitude less active than chloroquine or the best agents that they have, but it's a start. And so those results are stored here. And something really neat that actually has happened just last week or 2. So what's the point of making all this stuff totally public? Well, you get contacted by people that you totally don't expect. Brent Friesen, at Dominican University, he runs the sophomore teaching lab. And he was interested in having his students do, something more interesting than just repeating experiments that they've been repeating for 20 years that everybody knows the answer to. And he thought maybe the Yugi reaction might be useful for that. So he contacted me, and we talked for a little while, and we determined that this would make sense. And so he just wrote his manual for the spring for Chem 254, and it is the Yugi reaction. And his students are going to be doing new reactions that we haven't done yet, and we're going to be testing those compounds against malaria. So that would be really neat to be able to include students taking regular teaching labs. It's a whole untapped resource. It requires some more time, it requires some more dedication from people who run the teaching sections, but this could be very, very interesting, and it could be very motivating for the students. There have been some other people doing open notebook science. A student from Gus Rosania's group was here earlier. He's a collaborator with us. He's going to be studying the drug transport models for our compounds in the parasite and the red blood cells. Cameron Nyland, University of Southampton, has also been doing open notebook science. He doesn't use a traditional wiki. He uses a modified blog for his. And I'd just like to end on this slide where I think science is headed. We've been living in a world where science, the only point of communicating it was really for other humans to understand it. And we're getting to this really interesting time now where we can have actually human beings collaborating with machines if the human beings choose to make information available to them. And I think that's how we're going to get to this point where we can have machines actually doing real science, formulating hypotheses, testing them, analyzing the results, and then planning the next experiment. And I think to get to that kind of situation, we need to have free services. We need to have the possibility that anybody in the world can write a script that's going to try to process information and spit out something useful. And hopefully this is one way that we can actually get there. And I think it'll be very useful once we do. So that's it.
Okay. Thank you very much.